Welcome back to the Synthesis Workshop. I'm the host Xingeng Bai for today's Research Spotlight. In this episode, we are joined by Yannick Brägger on the topic of oxidative amination of unactivated alkenes forming amides and nitrides. Yannick obtained his bachelor's and master's degree from ETH Zurich, where his master's thesis was guided by Professor Tobias Ritter at Max Planck Institute of Core Research. He did his PhD in Professor Morandi's group at ETH Zurich, and he just passed his PhD defense in mid-September this year. Congratulations, Yannick. The floor is yours.
Thank you very much, Xingeng, for your kind introduction. It's great to be back on a synthesis workshop. In this presentation, I would like to showcase our group's recent work on the oxidative amination of unactivated alkenes via nitrogen atom insertion. Unactivated alkenes are prevalent soil materials in organic synthesis due to their abundance in petrochemical feedstocks and naturally occurring terpenes. Their accessible pi bonds make them valuable precursors for a wide range of transformations that install nitrogen. Among these, oxidative aminofunctionalization has attracted significant attention as a strategy for streamlining the synthesis of nitrogen-containing compounds, typically involving an amine source, an oxidant, and a catalyst. To illustrate this, I have depicted exemplary reactions developed by former colleagues in the Morandi group. Here, PONT, a hydroxylamine derivative, serves as both the amine source and oxidant in a single reagent. Combined with an iron catalyst, this approach enables the selective aminofunctionalization of unactivated alkenes, yielding primary alkyl amines. One significant advantage is the use of sodium salts for the functionalization of the conjugate position. While our group later published several protocol variations to enable different conjugate functionalizations, these methodologies lack modularity, accommodating only a narrow range of functional groups, like chloride or azide. This limitation arises proposedly from a rapid radical relay mechanism that quenches intermediate radicals via an iron ligand, restricting the compatibility of functional groups based on their bond dissociation energy with the iron complex. While these circumstances hindered further progress in aminofunctionalization, we turned to the literature with the aim to explore novel reaction mechanisms that could allow us to circumvent the challenges at hand. While scanning the literature, we realized that, while much effort had been contributed to explore aminofunctionalization of the pi bond of unactivated alkenes, methodologies that completely cleave the alkene while installing nitrogen in the same step appeared to be very scarce. This gap seemed unexpected given the widespread application of ozonolysis in both academic and industrial settings. The reason for this is the fact that ozone can be generated inexpensively and engages in a very fast dipolar cycloaddition with unactivated alkenes, even under cryogenic conditions. This leads to remarkable functional group tolerance. Additionally, the ability to vary the conditions under which the secondary ozonolites are quenched results in a highly modular reaction, being able to provide a wide variety of different reaction products. Motivated by this, we envisioned reaction conditions mimicking the oxidative cleavage mechanism of ozonolysis, while at the same step introducing nitrogen. We were initially inspired by a seminal report by Gassmann and co-workers, which explored the solvolysis of N-chloroaziridines in water. At elevated temperatures, these species underwent a disrotatory electrocyclic ring opening reaction, furnishing so-called azaylenium salts. Quenching with water then yielded the corresponding aldehydes as more traditional ozonolysis products. While this report only postulated the existence of these azaylenium salts, we hypothesized that under the right reaction conditions, we would be able to generate them in situ by direct nitrogen atom insertion into unactivated alkenes. Our approach would require a nitrene-bearing leaving group. The nitrene could undergo a 2+1 cycloaddition with the alkene, furnishing an activated aziridine, which is then proposed to spontaneously undergo electrocyclic ring opening, furnishing the azaylenium salt. This salt would then be quenched by suitable nucleophiles such as ammonia, followed by cleavage of the ensuing hemiaminal to generate two imine fragments, constituting formal aza-ozonolysis products. While the generation of a leaving group bearing nitrene seemed challenging, we were lucky that our group had some experience with such species. In 2022, a brilliant former colleague, Dr. Julia Reisenbauer, had developed a nitrogen atom insertion into TBS-projected indoles using so-called iodonitrines, which were generated in situ by combination of a hypervalent iodine source and ammonium carbamate. This reaction proceeded efficiently with remarkable functional group tolerance, which is shown on the selected scope example of pindolol. As a result, we were conscious that in situ generated iodonitrines would be ideal reactive species to engage with unactivated alkenes for our proposed reaction. Unfortunately, however, it was evident at the outset of our efforts that unactivated alkenes lacked sufficient reactivity, often acting as inert spectator functional groups in prior studies employing mixtures of hypervalent iodine and ammonia.
As anticipated, when we subjected 1-Dicene, our model substrate, to a combination of PFA, a hypervalent iodine source, and ammonium carbamate in wet methanol, no conversion of the starting material was observed. We selected wet methanol as the solvent based on the hypothesis that transiently formed oxalenium salts would be quenched by water to produce aldehydes, which are easily identifiable via NMR spectroscopy. However, we speculated that the high nucleophilicity of methanol might be suppressing the desired reactivity. In reactions involving nitrogen atom insertion into indoles, substrates that are typically electron-rich and highly reactive, it has been proposed that the reaction with iodonitrines is kinetically favored over solvolysis. Conversely, the lower reactivity of plain aliphatic alkenes led us to hypothesize that a less nucleophilic solvent might enable the desired transformation.
Switching to wet acetonitrile did not yield the expected product either, but for the first time we observed partial conversion of the substrate, resulting in 10% of the corresponding dehomologated nitrile and 11% of the epoxide. While we found the epoxide less interesting, we were excited about the nitrile because it served as a proof of concept. We hypothesized that the desired reaction steps were indeed taking place: iodonitrine generation, 2+1 of the alkene, followed by generation of the oxalenium salt. Quenching with excess ammonia would yield an imine, which instead of being hydrolyzed by water in the solvent, was oxidized by excess hypervalent iodine reagent. Since the generation of iodonitrines in situ necessitates the use of excess reagents, observing an oxidation event of the imine to the nitrile was not surprising. With this proof of concept, we went ahead to optimize the cleavage of unactivated alkenes to the corresponding nitriles. Switching from acetonitrile to even less nucleophilic solvents, such as trifluoroethanol and hexafluoroisopropanol, henceforth called HFIP, together with using higher excess of PFA and ammonium carbamate, enabled full conversion of the starting material and close to quantitative yield of the nonitrile product 1A. Interestingly, HFIP is so acidic that ammonium carbamate spontaneously decarboxylates upon dissolution, furnishing a clean solution of ammonia. During the optimization, we realized that we could also use HMDS instead of ammonium carbamate, which we hypothesize also decomposes to ammonia in situ by a reaction with HFIP. The slightly less reactive but cheaper hypervalent iodine reagent PEDA also enabled the reaction, but a higher excess is needed for full conversion. With the optimized conditions in hand, we went ahead to test the functional group tolerance of the reaction.
Here, I was very lucky to have two great colleagues, Ben Sebotlik and especially Anne-Sophie Paschke, to greatly contribute to the investigation of the scope.
We saw that internal alkenes are cleaved symmetrically, independent of stereochemistry. Alkynes, terminal or internal ones, are cleaved as well, but with low conversion and low yield. We are currently unsure about the mechanism involved with these substrates, but investigations are currently ongoing. Next, we tested ester and alcohol substrates. Both gave the corresponding nitriles in high yield. Notably, we did not observe any oxidation of the alcohol. Next, we investigated alkyl halides 8 to 10, since alternative synthetic approaches using SN2 type cyanation are difficult due to product mixtures. Unprotected amines are unfortunately not tolerated, but Boc-protected aminoalkenes cleanly give the corresponding nitrile. Next, we saw that heterocycles, somewhat sterically hindered alkenes, oxetanes, phthalamides, acetamides, epoxides, and a alcoholic acid alkenyl ester all gave the products in good to high yields. On the example of methyl jasmonate, we observed that chiral centers next to ketones are not epimerized. Piperidine, bearing a diene, was cleaved at the more electron-rich position to give both nitrile fragments in moderate yield. Cyclohexene gave adiponitrile as a sole product, which we could cyclize in a Torped-Ziegler reaction, demonstrating that we can use our method for an oxidative ring contraction in 2 steps. To show the amenability of our protocol to molecules of interest to the medicinal chemistry community, we further showed that pyridines, pyrimidines, quinoxylines, and quinolines are tolerated under our conditions. Finally, we showed that drug-like molecules also engage in the desired oxidative cleavage reaction to cleanly give the corresponding nitrile derivatives. When we reacted 1,1 disubstituted alkenes under our conditions, we were surprised. we saw a nice looking deshielded triplet on proton NMR, which looked similar to the nitriles that we typically obtained in the previous scope. Despite the fact that the reactions with branched alkenes again were very clean, initial attempts to isolate the products failed, simply nothing eluded from the silica-loaded flash columns. After a series of tests, we found that these new products could be extracted into DCM and reacted with Martin sulfurane, furnishing these sulfilamine-like products, which we could isolate as their TFA salts using flash column chromatography. At around the same time, we exposed exocyclic alkenes, such as methylene cyclohexane, to the reaction conditions, from where we obtained caprolactam in close to quantitative yield. These combined results revealed that we form amidines, constituting a nitrogen atom insertion process into a carbon-carbon single bond, while concomitantly oxidatively cleaving the alkene. While for linear alkenes, the amidines are stable species, the cyclic amidines are prone to hydrolysis, yielding instead the corresponding lactams. We then proceeded to test the scope of this unusual transformation. We found that using basic or neutral alumina could prevent the hydrolysis of cyclic amidines, at least partially. We quickly realized, however, that amidines are highly polar species that require 20 to 100% methanol in DCM to elute using flash column chromatography. Proceeding with the scope, linear aliphatic branched alkenes yielded the corresponding linear amidines in high yield. Alpha-methylstyrene, constituting an inexpensive commodity chemical and byproduct from the Commun process, gave the corresponding N-phenylamidine in high yield. For this substrate, the use of TFE instead of HFIP as a solvent was key to prevent undesired polymerization of the star material. Next, we evaluated several naturally occurring terpenes under our reaction conditions, including nutcatone, TBS-protected isopolygol, and dihydrocarbiol. All of these star materials contain isoprenyl groups constituting convenience substrates that provided the corresponding amidines in high yield, with exclusive reacher selectivity and excellent stereo retention. Nutcatone is particularly noteworthy as the oxidative cleavage occurs at the more electron-rich alkene with exclusive selectivity. Monocyclic terpenoids bearing electrophiles in the 3 position with respect to the isoprenyl group, such as dihydrocarbone or limonene oxide, also gave the corresponding amidines. In these cases, however, we observed cyclization upon intramolecular nucleophilic attack, either spontaneously or upon heating in methanol, forming bicyclic compounds. Finally, we were able to demonstrate that betulin and betulinic acid, as more complex examples, also yielded the corresponding amidine products.
Our working hypothesis for the reaction mechanism involves the in situ formation of an iodonitrine species or a synthetic equivalent thereof by combination of the hypervalent iodine reagent with ammonia. After formal 2+1 cycloaddition with the unactivated alkene A, an activated aziridine B is formed, which engages in an electrocyclic reopening reaction in a disrotatory fashion, furnishing acetylenium salt C. Being cationic species, these can easily be detected by ESI-MS experiments. If a suitable nucleophile is in proximity of the alkene, such as in isopolygol, the alcohol is able to trap the acetylenium salt in an intramolecular 6-endotric fashion, furnishing labile species 48A. These can be hydrolyzed with a mild basic aqueous workup or reduced using sodium borohydride to form 1,3-oxazenanes. Typically, however, when there is no nucleophile in direct proximity, ammonia quenches the acetylenium salt intermolecularly, forming hemiaminal-D. Hemiaminals are labile species, quickly undergoing CN bond cleavage to furnish imine E. Subsequently, we hypothesized that they coordinate to another equivalent of hypervalent iodine to form an N-electrophilic imine F. We were able to trap these species, for example, in 49, constituting a Boc-protected butynylamine, in which an N-bond formation was observed, yielding dihydropyrazoles as the major products. It is remarkable that aromatization was not observed despite of the excess of oxidant, and that these compounds are very challenging to access otherwise. Further, when aromatic rings are in proximity of the alkene, we observed electrophilic aromatic substitution followed by an oxidation aromatization sequence, furnishing quinolines. Again, it is remarkable that our method involves the construction of 3 CN bonds in one transformation.
Now progressing from the N-electrophilic intermediate F, if R double prime is a proton, we propose a stepwise oxidation to form the nitriles. If R double prime is an alkyl group, such as in the terpenes, we propose a Beckmann rearrangement that accounts for the excellent stereo retention in the terpene-derived amidine products. We hypothesize that this Beckmann rearrangement is initiated by hydrolysis of the N-iodine bond, an intermediate G2 involving an adenium intermediate that quickly rearranges the more electron-rich carbon-carbon bond with exclusive regioselectivity over the less electron-rich one, leading to exclusive migration of the methyl group in these terpenes. This process delivers the nitroleum cation I, which then typically is quenched by excess ammonia and yields the corresponding amidine. In dihydrocarbiol, where the alcohol is located a bit further away from the alkene relative to isopolygol, we observed formation of 52A as the exclusive product of this reaction, following an intramolecular 6-endodick trapping event of the nitroleum intermediate. This finding is again remarkable since all three substituents must be in an axial position for this trapping event to occur. And it concomitantly also demonstrates that these intramolecular trapping events, even if sterically disfavored, can outcompete intramolecular quenching by ammonia. We hypothesized that the hydrogen bonding network from the A-trip solvent drastically reduces the nucleophilicity of ammonia, which slows down reactivity and enables all of these steps involving highly reactive intermediates to be formed along the mechanistic pathway. Having established a suitable mechanistic proposal, we wanted to demonstrate the versatility of the amidine products that we isolated in the second scope. Amidines, while relatively rare in the literature, constitute interesting bioisosters to amides, ureas, or guanidines, with significantly different properties. We were able to convert amidines to the corresponding amides with mild saponification conditions. Unfortunately, when milder saponification conditions are applied, we typically observed moderate yields of the corresponding amides due to an unselective reaction, giving a mixture of amide and primary amine. Quenching the mixture with acetic anhydrides then typically gave the corresponding amide in high yield. Applying harsher conditions, heating up to 80 degrees over 24 hours, yielded the primary amines as the exclusive products. Highly stereo and sp3 enriched amines, such as the product 42C, constitute important building blocks for medicinal chemistry, and with our method, we can access these amines in 2 dump and stir steps, offering a significantly shorter synthetic route while conserving the stereo information. Lastly, we developed a slightly modified protocol that includes a combination of potassium phosphate and commercially available 15N labeled ammonium acetate instead of ammonium carbamate. This enabled us to access 15N labeled analogs of nitriles, amidines, acetamides, and primary amines through saponification thereof, as well as the majority of the trapping products shown previously. Thus, our method serves as a unified approach to rapidly access a plethora of 15N labeled nitrogen-containing compounds. To conclude, we have developed a highly general oxidative amination strategy of unactivated alkenes, cleaving linear alkenes to nitriles and branched alkenes to amidines. The process does not require exclusion of water or air, the setup is simple, and the reactions are clean and highly functional group tolerant, mirroring traditional ozonolysis. The mechanism involves the formation of acetylenium salts, which can be accessed by the insertion of a single nitrogen atom into unactivated alkenes, showing for the first time that acetylenium salts are versatile synthetic intermediates. The mechanism is supported by various trapping experiments, concomitantly demonstrating that our conditions can deliver a plethora of nitrogen-containing heterocycles. Last but not least, we could show that our method can grant rapid access to 15N labeled molecules. Obviously, this project would have not been possible without the contribution of numerous people I would like to thank here. I would like to thank my advisor, Professor Dr. Bill Morandi, for his support and mentorship. Further, I would like to thank Dr. Julia Reisenbauer and Florian Rupp for valuable discussions and suggestions. This entire project was a team effort, solely enabled by fantastic collaboration with amazing colleagues. I would like to point out Anne-Sophie Paschke for a tremendous contribution to the substrate scope and the saponification studies. Likewise, I would like to thank Bence Botlik and Benaya Kohli for their contributions to star material syntheses and substrate scope. Further, I would like to thank 2 of my former project students, mainly Francesco Felician, whose efforts resulted in the discovery of the reaction, and Nima Naziri, who meticulously optimized the reaction conditions. I would also like to acknowledge ETH Zurich for funding, as well as its technical staff. Lastly, I would like to give a special shout out to Michael Solar and Niels Trapp, our department's X-ray crystallographers. Their rigorous support significantly accelerated the progress of this project, especially the mechanistic investigation.
Finally, I would like to thank you again, Xingfeng, for your invitation and the audience for your kind attention.
Thanks to Yannick for sharing with us this interesting and useful chemistry. Hopefully you were inspired by his lecture. Please check out the published science paper he presented in this episode for more details. and don't hesitate to contact him if you want to discuss chemistry with him. You are also welcome to leave your comments here. Just don't forget to press the thumb button and subscribe us. See you next time.